Hello! In this video, we will be reviewing our module on chemical kinetics, specifically the rate of reaction. Consider first the general reaction shown on the screen. In this reaction, A and B represent the reactants, while C and D represent the products. Furthermore, the small letters A and B represent the coefficients of the reactants, while the small letters C and D represent the coefficients in the balanced chemical equation for the products. The rate of reaction R tells us the speed at which a reaction proceeds to completion. The symbol for the rate of reaction is R, and the unit of the rate of reaction R is molar per second, that's capital M per S, or it can be written as mole per liter times second. The rate of reaction cannot be directly measured. However, we can be able to measure it as either the rate of disappearance of the reactants A and B, as shown on the screen, or it can be computed as the rate of appearance of the products C and D, as shown on the screen as well. Note here that for the rate of disappearance of reactants, we put a negative sign before the delta terms. The negative sign here indicates the following. Namely, that since the reactants are being used up in the reaction, the rate of disappearance should have a negative sign. That is to say, the amount of the reactants A and B are decreasing as the reaction progresses. Meanwhile, for the value of R, in terms of the rate of appearance of the products, we notice that there is no negative sign here. The reason being that the rate of appearance of the products, the one inside the squares, should have a positive value. The reason for this is that the products are being made in the reaction. Therefore, as time goes by, the amount of C and the amount of D is increasing. As an example, let us consider the following balanced chemical equation: 2A plus 3B producing 4C and 1/2 B. The first question we are asked is to express the rate of reaction R in terms of the change in concentration of each of the reactants A and B and the products C and D. Letter B, when the concentration of D, notice here that the product D is enclosed in the square bracket. The square bracket indicates that we are talking about concentration. So when the concentration of D is increasing at 2 mole per liter second, how fast is the concentration of A, the reactant, decreasing? For letter A, our answer is as shown on the screen. So notice here we have the following. So let's focus first on our reactant A. Our rate of reaction R is proportional to the rate of disappearance of A as a reactant. So namely, R is equal to negative 1/2 times the rate of disappearance of A with respect to time. Now let's break down this term in here. The negative sign indicates that we are dealing with a reactant whose amount is decreasing over time. The 2 in the denominator in this coefficient comes from the coefficient of A in the balanced chemical equation. Delta A over delta T represents the rate of disappearance of the reactant A. Now we can write the same thing for our reactant B. Notice that in the balanced chemical equation, the coefficient of B is 3. Therefore, in this equation here, in letter A, we then get negative 1/3. Again, the negative sign indicates that we are dealing with a reactant, and delta B over delta T represents the rate of disappearance of the reactant B. Now, moving on to the products, we have the following. So we have 1/4 delta C over delta T. Notice here that there is no negative sign. The reason being that our C is a product. And furthermore, The value of 4 here comes from the coefficient in the balanced chemical equation, which for C is equal to 4. Delta C over delta T represents the rate of appearance of the product C. And finally, for our product D, we then have the following. Now, how did we get our value of 2 right here? So we have the following. So recall from your discussion on complex fractions, if you take the reciprocal of the coefficient for D, you'll get a complex fraction 1 over 1/2. And if you plug that into a calculator, or if you apply the rules in complex fractions, this now becomes 2. So that is the rate of reaction in terms of the change in concentration of the reactants A and B and the products C and D. Now we are free to answer the letter B. So let us now find how fast the concentration of A decreases if D is increasing in concentration at 2 mole per liter second. We utilize this equation in here, just looking at the terms for the A and for the D and equating them together. Now substituting the value given to us in letter B, which is that the rate of the appearance of D is 2 mole per liter second, we then have the following. Now dividing both sides by -1/2, we will then be able to get the value of the rate of disappearance of A. So dividing everything by -1/2 then, we get the value of -8 mole per liter second. The last question in this sample problem is as follows. If the rate of appearance of the product D with respect to time is 2 mole per liter second, we are asked to calculate the rate of reaction R. To do this, we once again utilize the equation that we wrote in letter A, and then we focus solely on the term for our rate of appearance of D. So from this equation, we then have R is equal to 2 times the rate of appearance of D with respect to time. And substituting the value of delta D over delta T, we then get the rate of reaction R equal to 4 mole per liter times second. Reading LG 2.1 to 2.3, we have learned that the rate of reaction R is proportional to the concentration of the reactants. This relationship between the rate and the concentration of reactants is given by the rate law. The rate law is a mathematical equation that relates the rate of reaction to the concentration of the reactants. Given the balanced general reaction shown on the screen over here, we can write the rate law as follows. So we have R equals to the rate constant K times the concentration of A raised to X times the concentration of the reactant B raised to Y. Notice that in the rate law, we do not write the concentrations of the products, only the reactants. The symbols represented here are as follows. K is the rate constant. The square bracket A and the square bracket B represent the concentrations of A and B at the given time, the units of which are in molar, that's capital M, or mole per liter. The exponent X represents the order of the reaction with respect to A, and the exponent Y representing the order of the reaction with respect to B. Now summing together the exponents X and Y, we will get the overall order of the reaction. As a sample problem, consider the following equation shown on the screen. By experimentation, the rate law for this reaction is found to be R equals to K times the concentration of CO raised to the power of 2 times the concentration of Cl2 raised to the power of 1/2. We are then asked the following. Letter A, what is the order of reaction with respect to CO? Letter B, what is the order of reaction with respect to Cl2? And letter C, what is the overall order of the reaction? To answer these, all we need to do is look at the rate law equation. As we've learned from the previous slide, the order with respect to a given product is simply the exponent. So for example, for CO, its exponent here in the rate law equation is 2. Therefore, our answer in letter A is 2. For letter B, the order of reaction with respect to Cl2 is just simply the exponent of the Cl2 in the rate law equation. Our answer for letter B then is 1/2. And finally, to get the overall order of the reaction, all we need to do is add up the exponents. So using our calculator, 2 plus 1/2 gives us 5/2 as the overall order of the equation. The exponents x and y in the rate law equation are not equal to the stoichiometric coefficients of the reactants in the balanced chemical equation, but rather they are determined experimentally. If we only have one reactant, which we shall call as A, we can then be able to make the following graph, and we can classify three major types of reactions depending on its order. For a zero-order reaction, it is characterized by the rate law equation R equals to K. Notice here that the reactant A is raised to the power of 0, and as we've learned from math, any number raised to the exponent of 0 is equal to 1. So K times 1 is equal to K. For a first-order reaction, it is characterized by this rate law. R is equal to K times the concentration of A, while for a second-order reaction, it has the rate law R equals to K times concentration of A squared. We also notice that we can be able to generate the following graphs to determine if we have a zero-order, a first-order, or a second-order reaction. We will use these graphs in a while. The relevant equations for the zero, the first, and the second order reactions are summarized in the table shown on the screen. In the second column, you have all of the rate laws for the zero order, the first order, and the second order reaction. The integrated rate equations, which we shall use in a bit, are also summarized here in the third column. The unit of K also varies with the order of the reaction. For zero-order reactions, the unit of K is molar, that's capital M, over the unit of time given in our data. For a first-order reaction, the unit of K is equal to 1 over the unit of time, while for a second-order reaction, the unit of K is equal to 1 over molar times time. The order of a reaction is determined through experiments. In the sample problem, we have gathered the following data, in which the compound AB is found to decompose according to the following reaction, namely, 2AB decomposes to produce A2 and B2. From the data gathered on the left, we are asked to first determine the order of the reaction by graphing, then write the rate law equation. After this is done, we are now asked to calculate the rate constant, and using the rate constant, we are asked to calculate the concentration of AB after 2 minutes. To determine the order of the reaction, we have to first make the graph based on the table that was given to us in the previous slide. Now let me draw your attention first to the concentration at time 0. It's 1 times 10 to the negative 4 molar. If we convert this one from power of 10 to decimal, the concentration is a very small value. That's 0.000100 molar. It's too small of a value to be able to graph properly. Now, in order to determine our order of reaction, we need to have a very accurate and a very legible graph. In order for our graphs to be accurate and legible, we have to make our graphs be the largest possible thing, preferably occupying the entire space of the graphing paper. To help us be able to do so, we can take the largest value of the concentration in the table, that's 1 times 10 to the negative 4, and divide this by the power of 10 of the smaller values. Now, since our largest value is 1 times 10 to the negative 4, we shall divide this one by 1 times 10 to the negative 5. 10 to the negative 5 being the power of 10 for the smaller values. Taking our calculator, we will then be able to get the following value. To generate a large enough and accurate enough graph, our calculator tells us that we need to have at least 10 boxes. Using our graphing paper, we now have the following. In the graphing paper, we mark off equal spaced intervals for the time in the x-axis. Each large square in here represents an increment of 5 seconds. So from this end of the first large box to its rightmost end, that's 5 seconds. Then from here to this place, we have 10 seconds, 15 seconds, 20 seconds, 25 seconds, and 30 seconds. It is important when making the graph that the increments are all evenly spaced. Otherwise, if the increments are not evenly spaced, we might have a graph that is misleading. We put the time in the x-axis. Now, as for the value of the concentration in molar, we will graph this one along the y-axis. Our computation tells us that we need at least 10 boxes. So therefore, we allot 10 boxes as shown in here along the y-axis, with the topmost part of the first box representing 1 times 10 to the negative 5, followed by 2 times 10 to the negative 5, 3 times 10 to the negative 5, and so on until we reach the topmost, which will then have the concentration of 1 times 10 to the negative 4. With our axes already marked down, we can then be able to plot the points in our table. So starting first with the first data point, it's 0 seconds with a concentration of 1 times 10 to the negative 4, giving us a dot right over here. Now filling in all the rest, for 2 seconds, we have the following. That's 9.3 times 10 to the negative 5. At 4 seconds, we have 8.61 times 10 to the negative 5. At 8 seconds, at 15 seconds, and finally at 30 seconds. Now, in order to determine whether this reaction is zero order or not, we take this graph and we make a straight line from the first data point, trying to connect through the middle of all of our dots that are coming after. Generating the straight line, called the least squares line, we then have the following. Again, notice that the line here does not pass through the points, but rather it more accurately comes between our points that we have graphed. Notice here that our dots do not lie within the straight line. So there are quite a huge number of them going away from the straight line. And since the data points do not lie in a straight line, we therefore conclude that this reaction is not zero order. We have already concluded that the reaction is not zero order. Now let us test if this reaction is first order. We have in here the data that was given to us in the problem, and to determine if it is first order, we have to first compute the ln of the concentration at each given time. For 0 seconds, we take the natural logarithm ln of the concentration 1 times 10 to the negative 4. Using our calculator, we find that ln of concentration of AB at time 0 is negative 9.21, and filling in the rest of our table, we now have the following. Notice here that we have negative values. So we start off with the least negative value at the top, and going down, we will have the larger negative values along the y-axis. Once again, we have on the x-axis the time in seconds, and on the y-axis, we then have the following. Again, starting off with the smallest negative value, and going down along the y-axis, we have larger and larger negative values. Plotting the values then, at time 0, we have the value of negative 9.21. That gives us a data point right over here. At 2 seconds, we have negative 9.28. At 4 seconds, it's negative 9.36. Then plotting the other data points at 8 seconds, at 15 seconds, and at 30 seconds, we now have the following. Once again, we generate the straight line graph called the least squares graph. In order to do so, we start off with the data point at time 0, and we make a straight line passing through the middle of our dots or our data points. The least squares line is the one shown on the screen. Notice here that our dots lie more or less within the straight line. This tells us then that our reaction is indeed a first order reaction. Now we can already stop at the graph for the first order reaction, but if we want to be really sure, we can also generate the graph for the second order reaction. In here, we have our table thus far, and for the fourth column, we are asked to be able to compute the reciprocal of the concentration, AB, which is our reactant. Using our calculator, we then find the following. Therefore, at time 0, the reciprocal of the concentration 1 times 10 to the negative 4 is equal to 1 times 10 to the power of 2. Doing the same for the other concentration values, we then have the following table already filled out. Now, the value of 1 times 10 to the power of 4 is a very large value, that's around 10,000, which is also too large to be able to graph properly. Now, in order to be able to deal with these very large values, we once again try to look at the largest value that we have and divide it by the powers of 10 of the smaller values. This should not be 3.39. This should be 2.95 times 10 to the power of 4 divided by the power of 10 of the smaller values, which is 10 to the power of 4. Now, using the calculator, we should get 3.39 boxes. But just so we can have a nicer and larger graph, we will then multiply everything by 10. So we need around 33.9 boxes to properly make our graph for the second order reaction. Once more, the value of the time is along the x-axis, all written down in equal increments. So we have 5, 10, 15, 20, 25, 30 for every box. And along the y-axis, we will plot the values for the reciprocal of the concentration. Again, when we try to plot these, we must plot them in equal increments so that we get the most accurate possible graph. Giving us the following then, each box along the y-axis represents a value of 0.2 times 10 to the power of 4. So starting with 1 times 10 to the power of 4, we go up, we have 1.2 times 10 to the power of 4, followed by 1.4 times 10 to the power of 4, and so on until we reach the topmost portion, which has a value of 3 times 10 to the power of 4. Now, plotting the values here for time and the reciprocal of the concentration, at time 0, the value for the reciprocal is 1 times 10 to the power of 4, giving us a data point around here. At 2 seconds, we have a value of 1.07 times 10 to the power of 4. At 4 seconds, we have 1.16 times 10 to the power of 4. At 8 seconds, 15 seconds, and at 30 seconds, we then have the complete graph. Now, to finally verify that this is a second order reaction or not, we start off with this data point here and we make the least squares line so that the line passes through the middle of the data points. The least squares line is as follows. Again, notice here that the data points do not lie within a straight line. This tells us then that this reaction is indeed not a second order reaction. In this portion of our review video, I would highly suggest you take the time to pause and try to be able to draw the graphs yourself so as to be able to practice how to be able to make the graphs and determine the order of the reaction. This sample problem might be helpful for you to be able to graph our number 4 in the alternative assessment. From the 3 graphs we were able to generate, we are now ready to answer letter A. The order of the reaction, according to the graphs we made, is a first order reaction. Since this is a first order reaction, the rate law is written as follows. Once again, the rate R is equal to the rate constant K times the concentration of the reactant AB. Notice here that we do not write the coefficient of AB, just the chemical formula of the reactant. So we have AB raised to the power of 1 since this is a first order reaction. Now from mathematics, we've learned that any number raised to the power of 1 is just equal to itself. Now having the order of the reaction and the rate law equation, we then now are ready to find the rate constant and the concentration after 2 minutes. In here, we will highlight the first order reactions. Since in our example, we have a first order reaction. Notice here that for a first order reaction, our K has the unit of 1 over time. We will use this unit of K to answer letter C. To find the value of the rate constant K, K is simply equal to the absolute value of the slope of our straight line graph. Now, from mathematics, we've learned that the equation for the slope is equal to the rise over the run, or that is y final minus y initial over t final minus t initial. Now, in here, for the first order graph, the final value is negative 10.29. This represents the y final, while the y initial is the value of negative 9.1. Plugging this into the equation, we then have the following for the numerator. So we have negative 10.29 minus negative 9.21, all of which is divided by the final time, that's 30 seconds, minus the initial time of 0 seconds. After plugging into your calculator, the value of the K should be negative 0.036 per second, but since we are taking only the absolute value, we disregard the negative sign, so K is equal to 0.036 per second. The unit of per second comes from the fact that our time here is in unit of second. So therefore, if the unit of the time given in the problem is in minutes, our answer should be in per minute. And furthermore, if this unit of time is in hours in the table, our unit of K should be in per hour. Now that we've computed the value of the rate constant, which is equal to 0.036 per second, we are now ready to answer the letter D. To answer letter D, we once again refer to the table, and for a first order reaction, we find that the integrated rate equation is as follows. So we take note of this equation in order to answer letter D. The beauty and utility of chemical kinetics, aside from telling us how fast or how slow a given reaction will be, is also that it tells us just how much of the reactant will remain after the reaction has started, given a certain number of time that has passed. That is what the integrated rate equation is used for. Now, to answer letter D, we summarize the following information given to us. In letter C, we have found the value of the rate constant K, that's 0.036 per second. And furthermore, we have learned in letters A and B that we have a first order reaction. The initial concentration is also written down. For our reactant AB, this value is 1 times 10 to the negative 4 mole per liter. In letter D, we are asked to determine the concentration of AB after 2 minutes. To solve this, we refer to the integrated rate law equation for the first order reaction. This is what we'll use to compute the concentration after a certain amount of time. Not the rate law expression, but the integrated rate law expression. For a first order reaction, the integrated rate law expression is the one that you can see on the screen. Substituting then the value of the K, the T, and the initial concentration of AB, we then have the following. So K is equal to 0.036 per second. That's our K. While for the term Ln, concentration of A sub 0, A sub 0 represents the initial concentration. The initial concentration is 1 times 10 to the negative 4 mole per liter. Now notice here that for the time, we do not input in 2 minutes, but rather we input in 120 seconds. The reason for this is that our K is in unit of per second. If we put in here 2 minutes instead, the unit of minute will not cancel out the unit of second. This will then lead to error. This is also one of the reasons why in our computations, we must always write the units every time so that we can double check if the units are canceling out and we can find if we are doing any errors in the computation. So we do not write 2 minutes in here, but rather we convert 2 minutes into seconds. Therefore, we get 120 seconds for the time. Now we can simplify the right-hand side of the equation. Using our calculator, we then have the following. The Ln for the concentration of AB after 2 minutes is computed to be equal to negative 13.53 after we have simplified the right-hand side. Now, in order for us to be able to compute the concentration of AB, we have to get rid of the Ln operator. Remember that in your mathematics, you might have already learned about something called inverse functions. An inverse function only serves to remove the operation, leaving us only with the term inside the operation itself. Now, the inverse of Ln is the exponential, so that's Euler's number raised to the value of negative 13.53. Thus, to get the concentration of AB after 2 minutes, we have Euler's number raised to the power of negative 13.53. In the calculator, we will be able to get the following value by inputting the following. The concentration of AB after 2 minutes is now found to be equal to 1.33 times 10 to the power of negative 6 mole per liter. Notice here that the concentration after 2 minutes has the unit same as the initial concentration. And notice further that the value of the concentration after 2 minutes is smaller than the initial concentration, which is exactly what we expect since AB is a reactant, and as time goes by, AB is being consumed, therefore its amount will decrease as the reaction is happening. To help you prepare for the first quarter exam, here is the coverage for that exam. So our exam will cover LGs 2.1 to 2.5. The LGs are already uploaded in K-Hub, and the PowerPoints are also available every week to help you be able to properly prepare for the first quarter exam. There are 48 points in total for the first quarter exam, and the types of questions that will be included in the exam are as follows. We have multiple choice, modified true or false. In the modified true or false, we have a statement with a word or a couple of words underlined. If the statement is true, you simply write capital T. And if the statement is false, you do not write F, but rather, you replace the underlined words with the words needed to make the statement true. And finally, we have the problem solving. In the multiple choice and the modified true or false, so we have to read our LGs 2.1 to 2.5 in order to prepare for this. So you might want to read upon definitions and the like to be able to answer the multiple choice and the modified true or false. Taken together, the multiple choice and the modified true or false is 24 points, while the problem solving focuses more on what we have discussed in this review video. So the problem solving amounts for the remaining 24 points in our first quarter exam. I hope this review video has helped you be able to prepare for our first quarter exam. Best of luck to all of you, and see you again next week.